Okay, let's cut to a completely different time and a completely different application. I want to talk about the development of web browsers in the 1980s and 90s. So, with the invention of the World Wide Web, there arose a situation in which we had a lot of different sites, which we call pages or sites. And we can just call those pages P1 through Pn. Now, that was great, but the next thing you need to have some way of searching through these pages to find the ones that you want. Otherwise, the pages are if you can't find the pages are useless, unless someone sends you a link to them, to one of them. And so the early web browsers just looked for keywords in context. Now, the consequence of that is they weren't very good. If you were interested in Paris, France, and you typed in Paris, France, what you got was a long list of web pages, including a couple from Seattle that recently went to France and took pictures of them standing in front of the Eiffel Tower, and that came up early in a keyword search because they said Paris, France a bunch of times. So that's not going to work. And as a matter of fact, the early web browsers, I was there, the early web browsers are very frustrating. They just produced lots of garbage. So something had to be done. So if you think about it, you don't want the couple from Seattle web page to be ranked highly. You want it to be ranked low because it's not important. But what does important mean? Well, the first people to come up with a really interesting example of that was two graduate students at Stanford named Sergey Brin and Larry Page. And they published an article in the journal Computer Networks called Anatomy of a Web Textual Searcher. And this is what they said, which is very interesting. The article begins, here we present Google, an algorithm designed to rank the importance of web pages. So what is their idea? What is an important web page? Well, you might say it's a page that is pointed to by lots of other web pages. And that's great. That's good. But it's not good enough. Because what you really want is pages that are pointed to by other pages that are themselves pointed to by many websites that are themselves pointed to by many websites that are themselves pointed to. In other words, they realized that we need to make a gigantic matrix, which is going to be n by n, where n is the number of web pages. And that matrix, Aij, is going to have a particularly simple form. Aij equals 1 if the site j points to the site I. So this matrix is going to start off as just a big mess of zeros and ones, depending upon whether the site J points to the site I. But then they had the same intuition Leontief had, which is what we want is not just sites that are pointed to, but sites that are pointed to by sites that are pointed to. In other words, if this is the matrix G, and we want to know what sites point to the sites that point to a given site, that matrix, by the same argument we just gave, that is the matrix G squared. And it's things that point to site I. So, needless to say, G squared is not good enough. They want to look at G cubed, ... They want to look at the long-term behavior of this points to. And we solve that regress by looking at, let's say, G100 and asking what is it's going to look like. Well, we know what G100 is going to look like because we've been saying this all along. G100 is going to be dominated by its principal eigenvalue and principal eigenvector. So what we are looking for is the long-term behavior, that is to say, the sites that are pointed to by sites that are pointed to by sites that are pointed to. And Brin and Page realized that what they are actually looking for is the behavior that dominates in a long-term iterated matrix. In other words, they needed the principal eigenvalue and the principal eigenvector. So in other words, let's say that an initial condition here is R1, let me just say Rn, where n is, again, the number of web pages. So this is a long vector. Nowadays, this vector has hundreds of thousands of elements in it, and you are talking about looking at a million by million matrix, which is very difficult to deal with. So we start with an initial condition where R1 is the importance of site 1, and Rn is the importance of site n. Then what we're going to do is we're going to update this importance by applying the points to matrix to it. And the points to matrix is going to be G, which is this 1,000 by 1,000 matrix applied to the vector R1 through Rn. And that's going to give us an update. And it's going to say upgrade R1 because page 1 is pointed to by many, many other sites that are pointed to by sites that are pointed to by sites. And that's going to uptick the value of R1. Conversely, if you have a bunch of zeros, which is saying basically nothing points to this page, then those zeros are all going to get multiplied in, and they're going to end up downgrading the weighting that is given to page n. So what they realized was the long-term behavior of this points to matrix is, like the long-term behavior of any iterated matrix, is domination by the principal eigenvector. So they extract the principal eigenvector. I think at the time they were dealing only with a 1,000 by 1,000 element matrix, which only has 1,000,000 elements. But still, you need serious computation to do this. But by 1995, serious computation existed. And they extract from that the principal eigenvector and the principal eigenvector is, because P1 through Pn are a basis for this high-dimensional system, then the principal eigenvector is going to be some A1 times P1 plus AN times Pn. That has to be the form of the principal eigenvector. And then all they want to know is, what is the biggest AI? Because the biggest AI is the website, let's say it's site 1, is the website with the highest weighting in the principal eigenvector. And this principal eigenvector is the PageRank. According to Google, your PageRank, the PageRank of site I is equal to AI, where AI is the component of Pi in the principal eigenvector. That is the most popular page. A2 is the second biggest. And so if you are a page, the PageRank that is assigned to you by the Google algorithm is the weighting that your page has in the principal eigenvector of the points 2 matrix.